Yeah, thanks a lot for inviting. Okay, yep. Recording under progress. Yeah, so thanks a lot for inviting me. It's a great pleasure to talk to you guys. It's also a great pleasure to see at least all the familiar faces alive, even though remote. It has been a terrible time for the last 2 years, no workshops, no nothing. And it is great that at least you guys maintain a regular seminar so that at least some discussion and exchange is possible in these difficult days. So now quickly, without, okay, the promotion is always a problem. Okay, outline. Outline first, I will give my talk is essentially about the ab initio approach to nuclear structures, the nuclear structure, and ultimately I will end up with focusing particularly on the intermediate mass nuclei, which are an unsolved problem. But let me not start with the end of my talk. So let's proceed here stepwise. So I will give first a brief historical overview of what has been done so far. I will summarize the current status and current problems we have. And I will review a few attempts to solve the problems. And since our problems are, of course, never solved, and in the end, I will encourage everybody to have some creative ideas. Okay, so history. History is a good thing because we must avoid being tunnel visioned. History opens our eyes. So believe it or not, I'll go back 50 years. This is the PhD thesis of John Nagele, which he did 50 years ago with Hans Bethe and Cornell. This is a publication of his PhD thesis in the Physical Review C1. And what I reprint here is just the first sentence. This is the first sentence of his thesis. And he says, one of the most fundamental and elusive problems in nuclear physics has been to understand the structure of finite nuclei in terms of, and he said, the nucleon-nucleon interaction, which is what you would say at that time, but today I took the liberty to insert what we might better say, namely basic forces between nucleons. But the point of the matter is, and why I cited here, so it's 1970, and naively people would say, well, 1970, that is just the beginning of microscopic nuclear structure. No, you have to see the subtlety. Elusive, you say elusive only when you have done something already for a while. So in 1970, believe it or not, people had already tried for 10 years to do microscopic nuclear structure and explain the structure of nuclei in this way. And already then it was elusive, but believe it or not, 50 years later, it's still elusive. So why? Well, the structure of why is fortunately very easy, but everything else will be difficult. Namely, as you all know, microscopic nuclear structure is based on two ingredients, namely quantum many-body theory and nuclear forces. And so when we have problems, it can only be one of the two or both. So let's see what it is. Let's start with the forces. So when we talk about forces today, of course, we talk about chiral forces. And the reasons are the usual poem here that I recite here, that you have heard 100 times, so don't have to recite here every line. But let me stress 2 points of the usual poem, which are important, namely, which in my opinion are the greatest advantage of using a chiral effective field theory. And that is, it allows for order by order expansion and in order by order uncertainty quantification. That is a great thing. And the other thing is it generates many nucleon forces. And as you all know, few practitioners all know, that is something that's very important. Okay, so then forces. So the forces, what are the forces? The chiral forces. Well, the chiral forces, as you all know, emerge order by order. And today, actually, the development has been done, believe it or not, all the way to N4 and 5LO. But don't worry, I will not go now through this order by order because the purpose and the reason is simple. The reason is that the purpose of my talk is not to put you to sleep in the early morning. So let's take a little bit easy here. Let's start with the first phase. The first phase of the development of nuclear forces, chiral forces, went up to 2 and 2LO, and there was a status of 2000, and there was few applications of that, but not much. With applications, there wasn't so microscopic calculations with chiral forces. There wasn't much right after 2000. So time went on, more the development of forces went to the next order, N3LO. And so this then characterized the status of the development of chiral forces of 2010. So now we're at 2010. And so the chiral two-body force is available up to N3LO, even three-body forces and four-body forces and N3LO were available. And there were some courageous people who actually applied all this. On the other hand, these lower forces here are really complicated. So, and not everyone can do that. And so the more realistic status of forces that are also in use of 2010 is that you would use, in those days, you would use typically the two-body force, well, to be even more precise, to use a non-local two-body force at N3LO and a local three-body force at N2LO. And that became kind of a standard model for a while. So I summarize it here. So non-local force up to N3LO, and then two-body force local, three-body force local and 2LO. And so that's the status of 2010 of the forces that were realistically, frequently applied in nuclear structure. And so the obvious next question is, what did people achieve with that? Now let's take it easy here. There are many nuclei, so let's first go to oxygen, and here's an overview of what was achieved in oxygen. This is actually, by the way, this is a figure that I stole from Heiko Hergert, and I hope he's in the audience, that I can finally ask him for his permission to use this figure to avoid a copyright lawsuit. But anyhow, so let's use this figure, assume here that he's so generous. And so what's this about? So it's all the oxygen isotopes, all the way from A equals 12 to 28, so pretty broad spectrum. Half a dozen of different many-body methods, same force, namely this is what I call the 2010 force. Yeah, I like short and concise notation. So what I just showed you before, circled in red, I call now the 2010 force. So 2010 force is applied. Half a dozen of many-body theories, all on top of each other and on top of the data. So when you go just to oxygen, all our many-body methods are reliable, and the force that was used at that time was also good. And I should note here the following: you could also produce the same plot where you use only one many-body theory, and then many different chiral forces. Yeah, you should also consider that. And let me just comment here in words. When you do that, you get actually a similar result. So when you use different chiral forces up to oxygen, then their results also essentially agree. I mean, they don't agree as much as what I show here, but they essentially agree. So important point to know for everybody who does nuclear structure and reads papers and wants to analyze it is, as long as you go only to oxygen, pretty much all forces agree. And so it is not discriminatory. If you want to learn more about forces, how good they are, and you go only to oxygen, that doesn't tell you much. And I stress that for the following reason, that even today, you often see papers where people have some new chiral force, great force, and to prove it, they do calculations up to oxygen 16 because maybe for some reason they can't go any further. They get great results, and the result is then we have a great force. Well, that you don't know when you go only to oxygen 16. That's 1.1 side remark that I want to make at this point. But now let's go on. So since we had then, after 2010, we had great progress in the field. And the nuclear many-body precision should be really lauded. Between 2010, the nuclear many-body theorists were very active, made great progress, and moved beyond oxygen and all the way to intermediate mass nuclei. And here I show you a typical from that time around 2010. Well, it's 2000, so my historical years are, of course, always plus or minus. And there has been a lot of work beyond oxygen to the intermediate mass nuclei around 2015, but I show you only one representative result by Strobeck and Heiko Hergert and others, because this shows everything that I want to mention. So the situation is, once you go to bigger, larger nuclei, is simply the following. Here, the first row are the light nuclei up to oxygen. So everything is on top of each other. All many-body methods, again, there's half a dozen of many-body methods here, all on top of each other. And you are on top also of the data. That means also the force. Again, this is what I call the 2010 standard force. The force describes everything well. But now comes the point, and that's the interesting one. When you go beyond, that means when you go to the intermediate mass nuclei, like calcium and nickel, down here, now we are down here, then the situation is the following. All many-body methods still agree. So the many-body methods hold out well also at heavier nuclei. However, we see this discrepancy, if my cursor comes back, yeah, between experiment and theory. And since the many-body methods are reliable, then it must be the force. So when people were able to go to intermediate mass nuclei, then the forces that were considered standard forces failed. That was an important, very important result that became evident around 2015. And so again, the light stuff is good, the heavy stuff, no good. And it has to be the forces, because the many-body methods work. So, so the forces had to improve. That's clear. That was a conclusion. The standard force isn't good. We have to improve. We have to work on the force again. And so after 2015, the typical development in our field was that a large variety of new forces erupted. And now let me go to some of them, because by systematically looking at what was now tried in terms of forces, we can learn something. So one force that was applied to solve this problem after 2015, I call it simply magic, because it's called magic in the literature. And it was developed by Kai Hebeler in 2011. It is the 2+3-body force. The 2-body force, he applied them in nuclear matter. The 2-body force, he constructed, he actually constructed, I should note, he constructed several forces, but I will, when I talk about magic, I mean only one force, and that is this one, the one that is commonly denoted as 1.8, 2.0, 1.8 refers to the cutoff of the 2-nucleon force in inverse Fermi. 2 refers to the cutoff of the 3-nucleon force in inverse Fermi. So this force gives, the 2-body component of this force gives this very attractive green dashed curve here, when you add the 3-body force, you get this fairly good saturation of nuclear matter. So that's magic. And this force was actually developed already in 2011, but it was not applied very much. But when this problem had become evident, that there was something wrong with the commonly applied forces, then suddenly some smart people picked this force up and said, hey, let's see how this force does. Maybe it does better. And yes, here again, the intermediate mass nuclei that failed in the previous calculation, they don't fail when you apply magic. So here's manganese, here's nickel, and the magic force perfectly reproduces the binding energies of a whole host of isotopes of those nuclei. And some people even went, so there have been many, many applications, very successful application of magic. I don't want to show them all, but let me just indicate here that people went all the way to tin. So just focus here on the on the red diamonds. The rest is of no interest. The red diamonds are the prediction of magic, and you see it's spot on up to tin. So problem solved. Yeah, problem was the overbinding. Sorry about that. And with magic, you don't have that anymore. So problem solved. You can go home. You're fine. No, not so fast. Magic is not a consistent. Yeah, I mean it's a chiral force. Yeah. So, but it's not a consistent EFT force because the 2NF is SRG evolved, and the 3NF is not. And usually when you have a SRG evolved 2-body force, you have induced 3-body forces, and these 3-body forces are left out. And so in this way, it's a little bit inconsistent chiral force. And to make this complicated description here simple, you could also just say it's not a purebred. Yeah, this force is not a purebred, to make it complicated, to give a simple name to a complicated story. And so the obvious question then, so I'm following here really a logical chain that people went through step by step. Then I go through it slowly, step by step, so everything is clear. So then, of course, the obvious conclusion is, well, can we then, we learned a lot from this, even though this is a little bit inconsistent, that means this magic applications were useless or bad or whatever. No, fantastic was to learn a lot. After all, nothing is perfect at this early stage in microscopic nuclear structure. But the conclusion is, of course, what I write here out in red. We have now learned how it should be, but can we now develop a 2+3, 2NF plus 3NF with similar properties, and which is consistently developed? And attempts have been made. Okay. I go now through a few attempts, not all of them, but those attempts which I perceive as particularly representative for the progress in the field. So one new force that had this goal that I just spelled out has been developed by Soma and Navati and others. I like short names for effective communication. So I call this the Soma force. The authors themselves call it the NN plus 3NLNL force. So since I don't like tongue breakers, I call it Soma. But still, this name tells you all. So the force is the following. It is the non-local N3LO 2-nucleon force from the 210 standard model. So they overtook that because they said, well, there's nothing wrong with that, boss. However, the problem with the older model was that the three-nucleon force has a local cutoff, and it's well known that the local cutoff for three-nucleon force causes trouble. And so they multiplied it in addition to this local cutoff with a non-local. So LNL means local, non-local. And it's the production of a local and non-local function is non-local, so it's a non-local cutoff. So the three-nucleon force, in contrast to the earlier versions, is now cut off by a non-local function. And there's great success. So again, these red curves are the ones you get with the local cutoff. So this is identical to the overbinding that I showed you before. Now, when they replace the cutoff with a non-local one, they move up to the green. Yep, they green up to green. So actually what is good in this work that it demonstrates very clearly how large the effect is of changing the locality of the three-nucleon force. Of course, it's also well known, this problem is well known, it's not that these guys didn't discover it for the first time, they just show it very clearly. As a footnote, let me remark that the change of a cutoff from local to non-local, when the change of the cutoff from local to non-local makes such a huge effect that is highly disturbing because it is not consistent with power counting, but that's a known problem. Nobody knows what to do about it. But since here in my talk, I'm not only interested in intermediate mass nuclei, also nuclear matter, they have not calculated nuclear matter, and so we don't know anything about it. And so we go on to somebody who has calculated nuclear matter, and that is Trisha. So the next model I discussed, I call simply Trisha Orbit, and there we do know the nuclear matter properties of the 2NF plus 3NF combination. So Christian Trisha constructed a whole family of N2LO potentials, a whole family of N3LO potentials that saturate nuclear matter quite correctly. And then this was applied in finite nuclei by Hoppe and others. That's why I call it Trisha Orbit. So let's look at this figure here. Forget about all the curves. That's just confusing. Let's focus to get a clear picture on what's important. Focus just on the orange band. Orange band are the predictions at N3LO with uncertainty. And these are the binding energies of nuclei from oxygen 16 to nickel. And so the results are here represented by this band. Experiment are the black bars. So there's a discrepancy of about 2 MeV, 25%. So nuclear matter is right. So the results of the Trisha Orbit model in a nutshell is nuclear matter is right, intermediate mass nuclei are underbound. Okay, next model, Hütter. So the group by Robert Roth did also some work. I call it Hütter because Hütter is the first author. And let's just focus here on the middle column of this figure that summarize the results. And again, what's plotted here, nuclei from oxygen all the way to nickel. And here they get the binding energies spot on, spot on, spot on, no underbinding. Radii, spot on, spot on, spot on. So they get the intermediate mass nuclei right, but with the parameters they use to get these results, also nuclear matter has been calculated, and nuclear matter comes out overbound. And so to summarize these two models that I just discussed, short and concise. So Trisha Orbit, nuclear matter right, intermediate mass nuclei wrong, Hütter, intermediate mass nuclei right, nuclear matter wrong. And so the $1 million question is, of course, can one get nuclear matter and medium mass nuclei right at the same time? So that is after these results, that's a problem. And these results I just presented are about 2 years old. They came out about 2+ years. And so this $2 million question was formulated also about 2 years ago. And as soon as this question was formulated, there came the answer. So here's the answer. So 2 years ago, the paper came out. And the title of the paper tells you everything, namely accurate by properties of nuclei from A = 2 to infinity by a chiral potential at 2L0. Infinity is, of course, nuclear matter. So accurate description of finite nuclei, including, of course, intermediate mass nuclei and nuclear matter, all done. So this is what the $1 million question raised. This is the description, the simultaneous description of intermediate mass nuclei and nuclear matter. And here are results. Let me show you some results. Oh, by the way, again, I like short and concise names for every model. So this model is called GO, but GO doesn't mean go. GO means GO, and GO means Göteborg, Oak Ridge. So two groups, two well-known groups, highly respected groups, have collaborated to obtain these results, and I will call it GO. And so here are the results. I mean, they confirm what the title of the paper says. So here we have nuclear matter. Of course, they make, like everybody, a few models. They use essentially two cutoffs. One cutoff is 394, one cutoff is 450. And sorry about that. And nuclear matter, yep, is right. Here, finite nuclei, intermediate mass nuclei from A = 40. So let's see, 60. The bands, the colorful bands, are the predictions by the GO potentials with uncertainty, and they are spot on the data. The black dots are, of course, the data, spot on the data. Also, the radii are great. Yeah, here the black are the experimental radii. The red diamond are the predictions by one of the GO potentials. They're all very good, and they're much better actually. They're, well, not much better, but they're better than magic. Here, the green stuff is magic. But notice that the scale here, the difference between the black curve and then these turquoise spots is about only 0.1 Fermi. So the difference looks big, but it isn't. But it is true, the magic, in spite of the great results by magic, I should note that at this point, the radii are a little bit on the smaller side, but whatever. So good. So GO potentials, everything is right, nuclear matter and intermediate mass nuclei, and so problem solved. Well, that's great, but it does raise the question, what did it? How did it? Because, I mean, Trisha Orbit are experienced people. They couldn't do a tutor, and the whole gang by road, experienced people, they couldn't do it. But these guys could do it. So what did it? What is the trick? What's the trick we missed? And so, well, the only way to find out is to do a systematic investigation. Now, before I do that, I have to make first a little excursion with you to explain how nuclear matter saturation comes about. So we need here for proper analysis of certain calculations, we need to understand how nuclear matter saturation comes about. So there's now a little excursion here. And let me mention again historically that nuclear matter saturation has been huge problems in the history of nuclear physics for 20 years through the 1960s and 1970s. For these 20 years, people have been desperately fighting to get nuclear matter saturation right. It was a huge topic. There were all kinds of ideas, but all the ideas failed, and nobody knew how to get nuclear matter saturation right. Then came the 1980s. In the 1980s, for the first time, nuclear matter saturation was explained quantitatively for the first time in history of nuclear matter theory, and it was explained. So I talk about something that's 40 years ago, it's the so-called Dirac-Bruckner approach. And what was found out in the Dirac-Bruckner approach is the following: the way to get it is you have to start from the two-body force that gives terrible overbinding, like take the lower dashed curve. That's a result from when you apply only a two-body force. Somebody's raised their hand.
Yes, I have a question, if I may, with this delta solution. Shouldn't be the delta degrees of freedom integrated out, and the description should not the description be in terms of nucleons only? I mean, after all, that's the whole idea of the effective theory.
Yeah, again, what should we integrate out?
Deltas are far. Yes.
Yeah. Okay. Yeah. Very good point. So you're referring to the fact that in effective field theory we have the delta full and the delta less? Is that what you're referring to?
No, I'm delta particles. Delta particles should not appear as the explicit degrees of freedom.
But in this Dirac-Bruckner approach, we don't have deltas.
No. I mean the solution that you referred to a moment ago, that this was the solution to have simultaneous description of light nuclei and infinite matter in this GO.
Solution. Yeah. As it turns out, I agree with you, by the way, because after all, it's an effective field theory.
Yes.
So that means you don't include every little crap. Yes. But it turns out, and that may comfort you, that the theory with deltas and without deltas gives the same results.
Okay.
When you go to N2LO, which is the lowest order, you should never work below N2LO. That's far too rough. Yeah. So that gives the same results, which means that since without deltas, life is simpler, then why not make life simple when you get the same results? So I fully agree with you. That's why, by the way, I personally never made potentials with deltas, except 40 years ago when they made the bond potential, but that's a different story.
Okay.
Thanks for the question. Yeah, so Dirac-Bruckner got for the first time nuclear matter saturation right. And again, the way it came about, and that's a very important point now, is you have first the two-body force contribution, and that has to be overbinding, that has to give too much binding. And then you add on that a super-duper attractive curve, a strongly density-dependent repulsive three-body force. And because what that does, it then, this lower curves gets then peeled up to here, which this peeling up shifts the saturation point, which comes also out far too high. Then the peeling up shifts it up to about the right region. So one method, actually the only one we know of, to get nuclear matter saturation right is a super duper attractive two-body force and then repulsive, strongly density dependent three-body force. But I mean, this is 40 years ago, by the way, this plot is 40 years old. And so, what was chiral forces? Well, it turns out chiral forces do exactly the same. This reference to history was not out of place. So how do we saturate nuclear matter with the chiral forces? Well, you start out with the two-body force that's far too attractive. Yeah, this one. This is just the two-body force part of your combination of two and three-body forces. Far too attractive. And then you add the three-body force. It has many components, but forget all these lines. These are all the different components. What only counts is the final result. So when you then added the entire three-body force and then 2LO, you get this solid curve. And that obviously saturates nuclei quite correctly. So again, also in the case of chiral forces, the secret of getting nuclear matter, you have to have a very much over-attractive two-body force, and then the chiral three-body force is automatically repulsive and highly density dependent, and that gets it right. Okay, good. So, and that's, by the way, true. I mean, we had already an example here, the magic force. So in the magic force here, this is the two-body force. You see, super duper attractive. And then when the three-body force is added, you are up here. And so let me plot this again. So this is again, by the way, here, this, see this two-body force thing. That's plotted here against KF, so now let me plot it against rho. So this green line is the same green line I just showed before, and that is just the two-body force contribution from the 2 plus 3-body force combination you apply. And now, so it has to be over-attractive, and it certainly is. But now comes another point, another very important subtle point. It is not enough to be super attractive. You have to be super duper attractive. If you also want to get the intermediate mass nuclei right, namely, what did Trisha Orbit get when you use only their two-body forces? Trisha Orbit's two-body force is also over-attractive, and whenever you are over-attractive, you can get nuclear matter right. So when you add to the gray curve some appropriate three-body force, you are here. When you add to this, you are here. That's not a problem. The point is now, the problem was, as you remember, are the intermediate mass nuclei. And if you want to get the intermediate mass nuclei, then it's important that you start from a super, not only a very attractive two-body force contribution, you have to start from a super duper attractive two-body force, like magic. Because when you start from this, add a three-body force and calculate intermediate mass nuclei, you get them right, as I've showed you. When you start from this, not super duper attractive, and add the appropriate three-body force, you get them underbound. And the reason is simply that the average density of intermediate mass nuclei is here. See my cursor? Here, below nuclear matter, here. That's where the intermediate are. And so, even though people say, yeah, but you have to use all these 2 and 3-body forces, and so isn't the combination the most important? Is the point that I like to make here, even though, of course, in the end, you apply a 2 plus 3-body combination. What you get is crucially ruled by what the 2-body force gave you, which you start with. When you start down here, then together with 3-body force, you're also very attractive. And so you get enough attraction for the intermediate mass nuclei, like magic does. When you start here, you do not have enough attraction in this region where the intermediate mass nuclei are located, and then you get underbinding like in the Trisha Orbit. So that's so much about nuclear matter saturation. And now let's turn to our topic. Our topic is to understand why the Go potentials are so successful. And so based on this consideration, or based on what I just explained to you, the curious question now is, of course, which everyone has back in the back of the mind, is now in this scheme here, where is Go? Well, let me show you. Go is red. In my talk, I have a color code. Everything that's red is Go. Go is here, right on magic. And so now it's clear why they get the good results. They are good as magic in terms of the two-body force. But we scientists ask questions and we go on. Namely, the next question is then, how come GO gets so much more traction in nuclear matter and Trisha Orbit doesn't? Well, what's the reason? Well, for that, you have to now really analyze the force in all detail. And the usual way you analyze forces, you look at the phase shifts, they predict, well, these red, again, my color code, keep in mind, my color code is very consistent to make things simple. Red is red and red is GO. So here are the phase shift predictions by the GO potentials, and some are fine, but some look a little bit concerning. Here, the 1p1 look a little bit. So again, the black symbols are the empirical phase shift analysis. Red curves are predictions. This is, of course, a little bit concerning. Epsilon also concerning. And but when I saw this, I wondered. When I saw the paper by the GO people, I got actually very excited, and I asked myself, how come I missed that there were some, obviously, with all due respect, some pretty discrepancies in the phase shift. How come I missed it? Well, the GO people do publish, of course, their phase shifts. These are the phase shifts. This is a copy from the publication. And let's just focus on epsilon 1. So this is epsilon 1, this is epsilon 1, and this is epsilon. Same thing. How come that's so different? Well, you can base a lecture on resolution scale for undergraduates on this. Namely, look at this. This goes from -2 to +4. So epsilon 1 goes over a range of 6 degrees. And in this plot, the plot range goes from -30 to +30, which is 60. So the quantity of 6 degrees is plotted over 60 degrees. So very small resolution scale. So this figure, the published figure of the epsilon 1 has just a very small resolution scale, so that you cannot resolve some structures that you may wish to resolve. But then there's another point to make. You still have to be careful here and not jump at conclusion. These are phase shifts. Phase shifts are not data. And what is very well known is that sometimes phase shifts look pretty bad, but describe the data well, and also vice versa. Phase shifts can look good and the data are very bad. And so this is not the final test. You have to confront the prediction of a potential always with the data to get a final answer. And so we did that. We calculated the chi-square, because after all, they could have found the new phase shift analysis. And we don't have to go over all the numbers here. Let's just focus on the circuit here in red. So again, I mentioned there are 2 GO potentials, one with 450, one with 394. Let's take just the interval 0 to 100, and the chi-square is 60. But no misunderstanding. This is not the total chi-square. This is the chi-square per datum 60, which, of course, I mean, with all due respect, well, the Nijmegen group always claimed you should get 1. So it's pretty big. And since I'm a senior person and like history, and since when I was a young graduate student, the most terrific potentials in the world were the Reed and the Hamada-Johnson potentials. So I asked myself, hey, what did these old potentials do? Well, here's the Hamada-Johnson potential. That guy gets 19 per datum. And so 60 years later, we get 60 per datum. Well, that is, of course, somewhat concerning, but still careful. Does it really matter in practice? Because you see what's well known. I mean, there have been so many calculations, all kinds of potentials in the world. And it has often happened in the past that, let's say, you take a Nijmegen potential, which has, of course, because the Nijmegen people were famous for their chi-square paranoia that had, of course, the chi-square of 1.0000. Then you take some Eindhoven potential where you would even bother to calculate the chi-square. And then you apply the nuclear structure, say ground state of some nuclei, and you get the same. So it is legitimate if you proceed here with sufficient care to ask, does it really matter in practice? So let's investigate that. So let's be a little bit focused for easy understanding. So let's focus here on 3 phase shifts plotted up to 100 because that's all what's relevant in nuclear structure. And now let's ask professional question. Namely, it's totally unprofessional to look at this. Totally unprofessional. Most people do. They look at it and say, "Oh, that looks bad," or "It looks good enough," or "What is good and bad?" These are ethical attributes. We are doing science. Now comes in as a gift of God that we deal with an effective field theory. And in an effective field theory, at each order, you have a truncation, a well-defined truncation error. And there's something else. There's a rule, or I would almost say a law, to an effective field theory, that namely at each order, the experiment that you want to explain with that effective has to be within the uncertainty of the prediction at that order. Yeah, so the uncertainties, so the closeness of the experiment to the prediction cannot be anything. The experiment has to be within the uncertainty at that order, at the specified order of calibration. And so the professional question asked, are these red curves within uncertainty or not? And we examined that. And it turns out, to make a short story short, so we have calculated the truncation error at 2 and 0, and then compared to this deviations. And to make it a long story short, so in the case of 1p1, these 2 curves are off by 22 and 40 truncation errors. Yeah, so ideally you should be off by 1 truncation error, maybe 2. We are generous, but that's about it. And so it's by 20. And then to take another example, 3p2, we are off by 7 and 5. So the bottom line is that the predictions of the go potentials are far outside the analog truncation error, and consequent, they are not consistent. Now we can make finally scientifically founded statement. So they are outside the truncation error, and they should not be that if they are a genuine N2LO potential. So there is now verifiably something wrong with these potentials. Of course, you can now raise all kinds of questions. We should really go to them. Namely, you could say the situation is now such, yeah, okay, these fits are not so great and even outside what they should be. Let's say you can't do better. That's it. And 2LO, you cannot fit better. So what do you do then? What you do then, if you're faithful to effective field theory means, is not to say, well, I can't do better and I'll go on. No, it has a meaning. It means your effective field theory is wrong. Throw it away, construct a new one, which is better, which converges to the experimental datum. But fortunately, that's not the case here. Fortunately, it turns out you can fit this, and we have done that. So here, you can also get fits like this. So again, color code, red is the original go potentials, green, blue. Blue are refits that we have done. So the blue theory here is exactly the same. I want to stress that. So the blue theory is exactly the same theory as the red. So N2LO with deltas, exactly the same mathematical expression, everything is the same, except every effective field theory, as you know, has a few parameters. and they are slightly adjusted in a different way, but only slightly. That didn't require much, and all coefficients are, of course, natural. So it is possible to fit NN scattering within the required uncertainties of N2LO, and potentials of this nature are the blue potentials. But still, we are not done. Still, you could say, yeah, okay, it would be better to have the blue fits because they are more faithful to the effective field theory you claim to use. But still, does it really matter? I mean, this difference, is it a lot with regard to nuclear structure application? I said before, sometimes some crappy potential of the past, ephemerological potential and the super duper knifing potential, they get the same. So still the question is, well, yeah, okay, the blue is better, but I mean, does it really matter? So, but again, does it really matter? And if so, how much? Okay, let's examine that. Let me finally come back to our, the center of our discussion here. So nuclear matter here, yep. We know again, green. When you're in green area, you get the intermediate mass nuclei right, and the gray area underbound. And the original go potentials are where you want to be, namely in the magic area. So, but now the red potential aren't that great, and you have to correct them, and the corrected potentials are the blue. And now when you use the correct blue potentials, what do you get within the scheme? That is now the crucial question, and we have calculated that. And so red is red and blue is blue. So when you apply the blue potential, bang, that's where you are, right in the middle of Trisha Orbit. So to summarize in very simple terms, so the goody-goody about the go potentials is that they are more attractive, they have more attraction than usual potentials, such that they get right into the magic area and get magic results. However, there's something verifiably wrong with them. And when you correct that, then the whole goody-goody extra attraction disappears, and you're exactly where Trisha Orbit were. And when you use now this correct N2LO potentials in nuclear structure, then I bet everything they will get again the same results as before, namely underbinding of intermediate mass nuclei. And the conclusion is the go potentials are not the solution of the problem that I had addressed. And so let me, since time is up, so let me summarize. The problem of describing nuclear matter and medium mass nuclei simultaneous is unsolved. Delta isobars do not create more attractive interactions. The delta full interactions are not any better than the delta less ones. So we are back to square one. And we have to start thinking again, tossing around ideas. Actually, the purpose of my talk, I want to start that we toss around ideas how to solve this problem. The problem is unsolved. And I toss around ideas here now, which I don't necessarily believe in, but that's the purpose of tossing ideas. So one may take a second look. For instance, one thing one may do, one can take a second look at what we call the empirical nuclear matter saturation. That what we consider the empirical nuclear matter saturation is based on 200 Skirm forces, which all then give about the same. But when you do ab initio, maybe it comes out different. Actually, a good example was the talk you had last week by Bruckner who talked about a different topic, but it's kind of an analogy. What he talked about is an analogy, what I'm indicating here, and he talked about the skin of lead. And what he showed is when you take a Skirm model, you can get easily anything. You can easily explain P-rex too. However, when you do ab initio, there are restrictions, and you can't get it. So you get it. The character of the results with ab initio is different to the character of the results with Skirm, and maybe it's the same here with nuclear. Anyhow, something I'm not necessarily claiming that, but something to think about. Then the non-locality and N interactions is a huge issue. It plays a big role. Magic has big non-locality, but it's due to the SRG evolution. And so the question is how to get substantial non-locality in the original forces. And that isn't easy. We have actually tried quite a bit in that direction, and it was not successful. The problem is simply that the Kyle-to-Pino exchanges, with or without deltas, they're always local. And the non-locality comes in only because you multiply with a non-local cutoff. And that, of course, does not generate per se a huge amount of non-locality. So that's a problem. Then there were some new ideas that were tossed around, combinatoric arguments promoted in the 3NF. Then, of course, yep, whenever we don't know what to do anymore, then, then we invoke the four-body forces, which we haven't applied. So are the four-body forces a magic solution? Something to think about. And then, by the way, there is another more general aspect. So I discussed only the saturation scenario where the two-body force is super attractive and then the three-body force is repulsive. And I didn't do that because I'm so narrow, because in the moment, it's the only scenario we know of to get nuclear matter saturation right. But in principle, let's start from scratch again. Why shouldn't it also be possible to start from a repulsive two-nucleon force and then get an attractive 3NF? Except nobody has found anything of that kind yet. And that is the end of my talk. Thank you very much. And I'm very happy when this could be a starting point of thinking, rethinking this issue, generating ideas, trying many things. Thank you very much again.
Thank you very much, Rup, for the interesting talk. I enjoyed it very much. So I have lots of questions and comments, but I think so we'll have the audience. So why don't we get started with the audience first? Does anyone have a question? Would like to ask it?
So maybe I can ask. So in the past, the saturation with before effective theory where it's either reached by three-body force or momentum dependence of two-body forces. So the momentum dependence, would that be the same as non-locality that you discussed?
Yeah, well, I think they're intertwined.
Okay.
But even the local forces have some momentum dependence. So yeah, I mean the chiral forces have quite a bit of momentum dependence, but some momentum dependence actually translates in locality and some not. It depends what type of momentum you're dealing with. Yeah.
Okay.
I mean, there are two types of momentum dependences. Actually.
So now with regard to the three-body force, you discussed the phase shifts and the quality of the description of the two-body data. But what about the three-body aspects of any of those forces that gave or did not give the solution?
Yeah, that is a very complicated issue. So we do not, the situation with the accuracy of the two-body forces and three-body forces is very, very different. So in the case of the two-body forces, we have a full theory and also full set of operators such that can describe all two-body data with a chi-square of 1. Now, in the case of three-body force, situation is totally different. In the case of the three-body force, we have actually indeed many three-nucleon scattering data, actually also about 4,000 or so. And when you take our current three-body forces like the N2 or three-body force and try to describe these 4,000 three-body data, you get a chi-square of 100 per datum. So the three-body force is in a very early stage. And therefore, you cannot argue and say, so some people try to argue and say that let's throw the two together. And well, when you have 4,000 data with chi-square of 1 and 4,000 data with chi-square of 100, you have a chi-square of 50. And so when the two-body force in some sectors has a chi-square of 50, so like the Go potential, what's wrong about it? But the thing is that when the chi-square of your entire force is 50 per datum, then when you want to translate it into percent error, I would guess, well, the error is probably plus or minus 50%, right? So when your input force, 2 plus three-body force input was 50 plus or minus 50%, then why do you want to get the results that are spot on? They should also scatter plus or minus 50% around. So this doesn't work that way. Yeah, one day, but that will take another 50 years. We will have, hopefully, a three-body force that describes the three-body scattering data, the 4,000 with a chi-square of 1. And then you can do it. But we are still, and then it's actually exciting to see if one gets nuclear matter and finite nuclei right with that three-body force that is adjusted to the 4,000 three-body force data. That will be a very exciting moment, but we have to be very patient because we are still far away from that.
Okay, thanks.
Thanks, Pavel. So the next one is Vitek on my list here.
Hi, Ruprecht. Very nice talk.
Yeah, hi, good to see you.
I have a question about the force calibration.
Yeah.
Okay. So when you have a two-body system or three-body system, the phase shift information is obviously crucial, because this is what determines, lots of issues into few body systems. But when you go to calcium 40, okay, then there's a lot of contribution from higher order forces, which are in the case of effective interactions, right? Simulated, say, by density dependence and effective changes of the low and coupling constants. I mean, is it proper really to base interaction, which is supposed to work for medium mass nuclei, primarily on phase shift and few body data? Don't you think that just for parity, you need to use rather massive amount of information on medium mass systems too, to determine those coupling constants?
Yeah, but yes, I fully agree with you. But these should not determine the two-body force, because for the two-body force, we have plenty of data just to pin them down. But but I agree with you that when you come to nuclei like calcium 40, that we currently restrict ourselves just to two and three-body forces. That may be the problem, because
that's exactly what I'm saying, Ruprecht.
Yeah, so the four-body forces, five-body forces may play a role.
You cannot just fit two-body force and freeze it, okay, and then to go to heavy systems. I'm saying that the parameters of two-body forces might be effectively changed if you go to heavier nuclei, right? Because of those many-body effects.
Yeah, but it's better to include these many-body effects, but include more many-body forces. So
this is a question of, it's a question of philosophy. So what you showed, is of course all correct, but is based on the assumption that you have well calibrated two-body force and you are very happy, and then you go on, okay? I don't think that you can do heavier nuclei in this way.
Yeah, but the thing is, that's a matter of philosophy. So when the philosophy, and you are very familiar with both, so it's good to talk to you. There are skirm forces. And in case of skirm forces, you are 100% right. Yeah. But ab initio, in my opinion, means two-body forces are pinned down by two-body data. Three-body forces are pinned out by three-body data if sufficiently available, and four-body forces by four-body data. And then let's see if we get it right. And when we get it right, we feel we have a more fundamental understanding of the explanation, as in contrast to when we get things right, when we from the outset already fit everything halfway to what we want to get.
But
So
if
that's
you,
the way I feel it.
in your philosophy, calcium-40 will require 40 body forces, right?
Yeah.
This is, well, good luck.
Yeah, right. but let's do one thing at a time. Next thing, forwarding forces. Yeah, but I get the point. Yeah, I get the point. There's certainly something to seriously think about.
Okay, thank you, Vitek. Any other question? Yeah, Jerry, please go ahead.
Yes, I enjoy the talk very much. I have just maybe not question, but slightly comment. So in your last item in this conclusion, you says maybe alternatives scenario, like you can have repulsive 2NF plus attractive 3NF. This is, in fact, we see that when we do higher cutoff. So on your page, previous page 28, 29, you mainly want the 2NN to be over attractive and then 3-body force to provide repulsive. However, this is only, this is a cutoff dependent statement. It's only true for me for low cutoff. Low means 450 or lower.
Yeah.
If you go like 600 MeV cutoff, I find it hard to find nuclei, even helium-4, correctly. If you have if you want the 2-body to be over attractive and 3-body to be repulsive. That's just a small comment. And I have a more general question. Is all the potential you mentioned is based on one power counting. That's one per power counting. So if in my opinion, if after so many years and people try a lot to fit up to NNLO or N3LO, and it doesn't solve the problem as you say, isn't it quite obvious that the power counting itself could be wrong, like as Dirac and Koch always insist. And maybe I believe that we need to really think other solution, like we need to use alternative power counting, which doesn't have this renormalization problem. And that's my own opinion. And
Yeah.
finally, regarding the fourth, oh, sorry.
Then go on. I want to
Oh, yes.
listen to the end of your comment.
Yeah, last comment is about the success of the Skirm force. So I noticed that if you take the density dependent term, the power of the density dependent term in the Skirm, this alpha, if that's, you take it to be 1. then it corresponds exactly to the three-body force. However, there are hundreds of Scrum force. Very few of them has the power exactly 1. So it's a hint that may be related to your one of the list in this conclusion page, that your three-body force is not enough. Maybe you need the four-body force to have the same or similar success as what Scrum has done. That's all. Thank you.
Yeah, I like your comments. And let me also dedicate to the power counting scheme. I agree with what. So in the moment we use a power counting scheme, which people often call the Weinberg counting, original counting, and as pointed out by you and also von Kolk, there are problems. There's problems with dates. And however, we practitioners of nuclear forces stubbornly, in spite of all these objections, which I do understand, we continue with using the old stuff of Weinberg in spite of all the concerns raised. And the reason is just a practical one. In the new and alternative power counting, it has not been easy yet to construct potentials. And that it's not only about the potential. These alternative schemes requires also that the many-body practitioners change their practice. Yeah, so for instance, one scheme is, okay, they can take the one final exchange, as I always did, just iterate it to all orders. The rest has to be perturbative. Now a coupled cluster guy will tell you, well, how do I do that? The one final exchange, I crank through all orders, and then what? How to get the other crap in? And also people are sometimes a little bit lazy and say, oh, I don't want to change my code. So, but you are right. There is a problem with power. So the power counting that all the calculations I presented are based on is questionable. And at least in the future years, we have to go through the pain also to take it more serious, to apply different schemes of power counts all the way to the many-body problem. Fully agree. Yeah. And then it's good to hear from you, Bernard. Did I stand you right? You have seen a scheme where you start from a repulse, is the last line of what I'm displaying here now. You have seen the scheme where the two-body force is repulsive and an attractive two-body force comes in. Is that right?
Yes, for higher cutoff, yes.
Yeah, okay, good to know. Well, we need alternatives. At least we need to check them out. Yeah, because we are stuck. Don't know what to do. Try everything. Yeah, thanks a lot. Great comment.
Thank you.
Thanks, Jerry. Anyone else? Okay, then just a comment. So, Rup, when you showed your calculations for the phase shifts on one of the previous slides, just wanted to comment that so my Buckeye collaborators and colleagues, Jordan Melendez and Sarah Veselowski, they have developed sophisticated Bayesian methods for quantifying EFT uncertainties for scattering observables. And so those tools are publicly available and can be used to quantify the uncertainties and make the plots accordingly. So you might find this interesting. Okay.
Thanks. But I believe, yeah, you're right. That's the future how to do it. However, I believe that when you do a proper Bayesian analysis, that's essentially what your comment is about, you will probably often get results that are not very different from the simple truncation error analysis which I presented. But it has to be seen. Yeah, it has to be seen as we ultimately can only confirm by doing real calculations.
Yeah. So I mean, this is part of the comment, but the main part was so I mean, as you pointed out in your talk, I mean, to compare a prediction or a calculation with the data, you need uncertainties, and in those they were not plotted. All I'm saying is that GSUM is the Python package called makes it quite easy to quantify and plot those uncertainties. And absolutely right, but if you can do it in the same amount of time with a full Bayesian analysis, then you don't need any other standard EFT uncertainty anymore. Okay.
Yeah. Good to know.
Anyone else? So if you don't mind, I would like to ask you a question or a few questions offline, but since we are already at 19 or 20 past the hour, let me thank you. Let me close the session and thank you, Ruprecht, again for this very, very nice talk. I really appreciate your time and giving this special nuclear theory seminar here. So as I said in the beginning, this is probably the last theory seminar in this session. So so I'll see you sometime soon, hopefully in August or so. And until then, take care. Bye.
Bye-bye. Yeah. Okay.